All right, today we're going to be talking about uniform accelerated motion. And before we get too deep into it, we will not finish what we need to talk about. We will do enough to successfully take the semester exam, but I will come back to this material after our break so that we have it fully explored in time for our AP exam. So what we are doing is kind of an abbreviated version. These are the things that I think you should be able to do for you to be successful on your test. So, or on the semester exam. But understand, I think that this is a little abbreviated. So what we're going to do is threefold. We're going to talk about what uniform accelerated motion is. We're going to talk about the specific details of what it means to calculate centripetal acceleration. And then we're going to apply it to an example from last week. So I want to start by saying this, that so far this year, when we've talked about accelerations, we've talked about the fact that they come from unbalanced forces that act to change the motion of an object. And we have focused that discussion on changes in speed. We've indicated that you can measure the effect of an unbalanced force by looking at how much an object changes, how fast it's going. So forces in the direction of motion help speed up an object, and forces against the direction of motion slow down that object. But how much its speed changes has been based on how much inertia the object has. And we've talked about changes in speed by looking particularly at changes in, we talked about changes in velocity by looking at changes in speed. But I need you to have a broader view. Acceleration isn't just about speed. Acceleration is about changes in velocity. And velocity is a vector. Which means that velocity has both speed and direction. The speed part is the magnitude. And we've kind of focused all of our discussion so far in the changing of speed. This is going to be a discussion about what happens when that force doesn't change the speed of the object, when that force changes its direction. So we're specifically going to be talking about accelerated motion, where the acceleration causes a change in direction. So instead of saying uniform accelerated motion, we're going to talk about uniform circular motion, where now the acceleration is about change in direction and not a change in how fast you're going. Now, there's at least give you a bigger, broader picture of this. When we've talked about an object so far and spent time talking about what that object might be doing, when we've indicated that forces act on the object, we've also often dissociated that from what the object's already doing. Meaning we've not talked about the fact that the object might be moving already. We've frozen the object at a particular moment of time, drawn a free body diagram, and then used that free body diagram to kind of highlight what the object's going to do. If the object's already moving, if it has a velocity, and you apply a force to it, well, some components of that force might act to change how fast the object's going, but some components of that force might act to change what direction it's going. Like right now, I think you should be able to understand that this force is both going to cause the object to go faster, because there is a component of that force that is this way in the direction of motion, but there's also a component of that force this way. And the component of the force that's not in the direction of motion causes the direction of that motion to change. So although we're going to focus on the change part for the next couple of days, we've already spent time focusing on the part that changes its speed. That was the whole discussion of dynamics, was about the parts of the acceleration that were in the direction of motion. So now we're not going to throw away this other part. We're going to talk about the parts of the acceleration that are perpendicular to the direction of motion. These parts cause changes in direction. But I want you to have the big picture. If you're writing your notes out and you're trying to keep accurate notes, a force can do both. Force can both change direction and change speed at the same time. So I'll repeat this just once more. The components that are along the direction of motion change how fast it's going. And the components of force perpendicular to the direction of motion change direction. But again, a force can do both. You can be changing how fast and direction all at the same time. We are going to now focus. In order to focus, let's consider just a simple object traveling in a, for the moment, a direction straight up with a velocity v. And let's say it experiences an acceleration to the left. Now, this acceleration has no component in the direction of motion, which means this acceleration is going to cause a change in direction. That change in direction is clearly going to cause the object's path to curve. It has to. It's going to bend the direction of the velocity to the left. Now, here's the thing. If the acceleration if the acceleration stayed the same and was continually pushing this way, then the object would be a projectile. We've already seen that, where we had an acceleration straight down, but it's moving sideways. It has a parabolic motion. But if we want the object to continuously turn, well, then we're going to want our new velocity to continue to change direction. To do so, that means my acceleration has to also change direction to match. I mean, if I want the object to travel in a circle, so maybe I'm going up and now I want to be going to the left, or I'm traveling north on Sheldon, but I'd like to be traveling east on Citrus Park Boulevard. Well, then I want a continuous change in direction from north to east. To do that, I'm going to have an acceleration that's going to continuously cause my car to change direction. So I can't leave the acceleration always the same. I need the acceleration to stay perpendicular to the velocity. So as that velocity changes, the acceleration is going to change too. This is a unique set of circumstances that produces a unique acceleration that is always perpendicular to the velocity. And if you look clearly at this picture, all of these accelerations tend to point to the same place. That place is the center of curvature. Meaning if you have an acceleration that is always perpendicular to the velocity, if you have an acceleration that is always perpendicular to the velocity, it will cause a circular motion in your object. If you have an acceleration that's always perpendicular to the velocity, it will cause circular motion in your object. This type of acceleration, we've given a special name. It's called a centripetal acceleration. And that name is important. It is two words, center pointing. A centripetal acceleration is a center pointing acceleration. Centripetal acceleration is not to be confused with the word centrifuge or centrifugal or centrifugal. These words are part of the popular lexicon about things that spin. So you can be in a centrifuge, you can experience a centrifugal force or a centrifugal force. These words don't have much business in this classroom. These are not real forces. They are not what you think they are. They are products of inertia only and don't really have have business when we talk about centripetal motion. So if you've heard these words before, they're real things, but they're not what you think they are. They're not a force. In fact, there is no centripetal force. There is no centripetal force. Put that big in your notes. There's not a new force here. So before we go on, in your notes, there is no centripetal force. For an object to travel in a circle, there must be an unbalanced force that causes centripetal acceleration. Learn that statement. I'll say it 2 more times. For an object to travel in a circle, there must be an unbalanced force that causes centripetal acceleration. For an object to travel in a circle, there must be an unbalanced force that causes centripetal acceleration. The only difference that we're going to add to Newton's second law is that we're going to say that if we know the object's traveling in a circle, we're going to say that it has a centripetal acceleration. We're going to put a little c here to tell us that this object is not speeding up, it's not slowing down, it's changing direction. So in any situation where the object changes direction, doesn't speed up or slow down, but changes direction, change this to a little c next to the acceleration. Because we have to calculate it different now. For an object that doesn't speed up or slow down, we can't use VF minus VI over T. This doesn't work anymore. The centripetal acceleration comes from looking at how fast the object is going and how big the radius of curvature is. This is on your equation sheet, by the way. You should probably find it. This is the calculation for centripetal acceleration. It's intimately tied in with how big the circle is that the object is moving on. Now, we're going to treat these problems different than we treated the force problems before, because the situation is different. In problems that involve centripetal acceleration, you still have all of the same forces that we've had before. There's no new forces. So when we list all the forces that have been in our problems before, things like gravity, normal, friction, tension. For something to travel in a circle, it's going to be some combination of these that causes circular motion. There's not going to be another force coming out of somewhere else to cause circular motion. It will be one of those or a combination of those. Everything that travels in a circle has to have an unbalanced force. This is how most amusement park rides make you feel accelerations. They don't do so by actually making you go faster or slower. They make you change direction. That's why most of your roller coasters have curves in them. Otherwise, if all they want to do is make you feel acceleration, they would just speed you up and slow you down. They don't do that hardly at all in these rides. They make you whip around, go left, go right. Do that a lot of times. That's how they make you feel accelerations. So let's talk. Before they redesigned it, when you were to make the turn from Sheldon to Citrus Park Boulevard, a corner that most of you are aware of, used to not be a road on that side. So if Sickles was this way and the Circle K was right there, you guys know where I'm talking about now? It's a bad intersection. I accident there about once a week. And part of the reason is because it's not a 90-degree angle. For whatever reason, they decided that Circle K had to stay there, and so Citrus Park bent around it. I don't know how long that Circle K has been there, but it must have been a long time for them to move the entire road around the Circle K. But let's be honest. The old way, there was a single left turn lane that would back way up at the end of the day. Most of you know about that, which is why a lot of you would just go over here, make a U-turn, and come that way, because you just would want to avoid this. But a few of you make this turn. There's a median right here. And I know they've added another turn lane. That's not to your advantage. And the reason I say that is because to make this turn, you had to come out here, and then the circle began after you left the intersection, because I'm sure you remember from your driver's test that when you make a left turn, you're supposed to go from the leftmost lane to the leftmost lane. Similar for making a right turn, you're supposed to go from the rightmost lane into the rightmost lane. So that car that's coming this way, they're supposed to turn like that. But I've seen you guys. This turn has a small radius of curvature. In order to make this turn, when you first enter the intersection, there has to be an unbalanced force acting on your car in this direction. It's the only way the car can turn if it has a velocity in this direction. That unbalanced force has to be here. Now, you might not understand what force causes that, but there's only 3 forces acting on the car when it goes to make the turn. It's not like it shoots out a harpoon and grabs onto something so it can make a spinning turn around this corner. Which means the 3 forces acting on the car will be weight, normal force, and friction. And the only one that can be sideways, it's got to be friction. You make this turn because of a frictional force. That's it. That's where you turn the wheels sideways, drive them into the ground, and let friction push the wheels to the side. There are no other forces that act on the car. I'm not like, there's nothing on the list. I mean, is there any strings or cables connected to the car? Is there anything pushing the car from the outside against the passenger door? There isn't. The only thing in contact with the car is the ground. And it can only provide a frictional force and a normal force. That's it. So friction causes your car to turn. Now, here's the thing. Friction has a limit because it's static friction, right? You don't want the tires to slide. So there's a maximum amount of available force. And that force causes centripetal acceleration. And it's very important to understand this. This has a maximum. You can't go over that. But you guys, I don't think fully appreciate that your velocity may not have a maximum. You think you can go as fast as you want in this turn. It's not exactly true. You can't. There's a finite amount of available friction, which means this ratio has a fixed maximum. If you want to make a turn with that radius, there is a maximum speed that you can make the turn. If you go faster, it will take more friction. If there's no more friction, you will not make this turn, because suddenly there will not be frictional force acting against the car's direction. You'll just slide. Now, many of you have hit that turn really fast. You'll hear your tires squealing. That's kind of a sign to you that you're at the threshold. Most of you hit the brakes. Dumb move. That's adding more pressure on your tires, more required frictional force, because now that has to turn you and stop you. There's a fixed amount. That's why this area happens to have a car in it almost once a week, because somebody goes to make that play and realizes not so much, and they slide into the corner there. Just look at that corner. Even though they've just barely redone it, it's already black from people hitting it. What you guys tend to do is if the top part of this fraction gets bigger, one way to compensate is make the bottom bigger too. To make the bottom bigger, then the fraction stays the same size. What does that mean? You kind of violate the rules. You don't turn in this way. You turn this way. You make the radius of curvature bigger. It's illegal, but it's better than sliding in the intersection. Now that there's another car here, though, you get less chances to do that, right? Because if they follow the rules and they go into the middle lane, there's no way you can go into the outer lane. It doesn't change the fact that this guy's probably playing the same game. A velocity too high, about to enter this intersection. Luckily for him, he has less of a turn to make, but he's still bound by the same rules. Same amount of friction, same amount of radius, same amount of velocity. You can't violate this. You might think you can, but you really can't. Unless your car is specifically designed to ramp up the friction because you've got lots of flight fins and stuff, like an Indy car or something. But most of the spoilers I've seen on your cars are just there for fun. They don't really do anything. Now, that being said, this is a discussion to remind you that the acceleration is a little different. When it comes to centripetal motion, it's about this combination. And I'll point out that every time you guys have been on a curved road or an overpass that has a turn, they have a posted speed limit. That speed limit is actually set based on the radius of curvature and the material that they built the road on. And then they've brought it down a little bit to keep it within a safe parameter. It's not arbitrary. Those numbers are calculated specifically based on this physics. Now, instead, what I want to do is I want to talk about a problem that is related to what we just did. And I want to use a roller coaster example. Something like the Scorpion, which has a nice, straightforward, dedicated 360 loop. Now, if you rode this, then you know that this ride is pretty straightforward, pretty benign, and pretty easy to ride. It's a good introductory roller coaster for little kids. Now, what I'd like you to do is pretty straightforward. I would like you to take a minute and consider that should you have seen this ride in action, and most of you have, then I would like you to tell me or draw. Why don't you draw what the free body diagram must look like on the car at these three locations, A, B, and C. Assume that the cars successfully make it through the loop and that we're looking at it where A is first, then B, and then C. All right, just take a minute and draw the free body diagram for that. Now, I should come by and take a look at all of your pictures, but I know who's playing along and who's not. If you're not playing along, we only have 3 days this week. So I'm packing it all in these 3 days. This is a test question, or it has been. So make sure you are understanding that we only have 3 days. The Mario Kart music is really fast right now. At A, I hope you drew 2 arrows. But I know that you guys don't always pay attention to the things I say. You kind of work in autopilot. I would have drawn the weight downwards. And just as a quick reminder, all of these will have a weight downwards. And all of those weights should be the same. It's not like the car is losing weight as it goes through the loop. If it is, that means people are falling out. Bad. However, the unbalanced force has to be towards the center. If I want there to be a change in the direction of motion, then the net force has to be unbalanced, and it has to be unbalanced to cause a circular motion, which means at A, the normal force should be upwards and should be greater than the weight. It's not accidental, it has to be this way. At B, there's going to be a component of force that has to cause a change in direction, the normal force. And there's a component of force that's causing the object to slow down, the weight. B is a little complex because it's slowing down and moving in a circle at the same time. So there's 2 forces that are there acting to cause both of those things. But at C, the normal force is also going to be downwards. All of these forces are going to try and contribute to change the velocity of the car. We will focus on A and C because the forces line up towards the center. We'll kind of leave out B because the forces don't line up towards the center, which means the car is slowing down while going to the side. But you should be able to, with the knowledge you have, tell me how fast it's going when it reaches A. You have the skill set to do so. Let's assume that the lift hill is 25 meters high, and the cars are going to make it to point A without losing any energy due to friction. This is last week's work. So take a moment. I will pick one of you in particular to tell me how fast the cars are going at A. So Francisco, how fast is it going at A? I'm patient. Although, can somebody at Francisco's table help him out? Because I'm not that patient. You got what? Anybody else get 11.2? Nobody else got 11.2. That's a big difference in 100 and 11.2. What did you get? 22.36. 22. We got 3 answers. There's a lot going on here. This is making me very worried for Thursday's test. I'd argue that there's gravitational potential energy here. How many of you would agree? That's not enough of you, and that's why you're going to have a problem on Thursday. I'm not going to feel bad at all. I think the blue line is the reference level, and therefore I have all kinetic energy at A. That seem good so far? Yes, sir? No worries. So MGH at A, I'm sorry, at the top there, equals 1/2 mv squared at the bottom. I think that's how we're going to do it. Cancel out the m's, and you've got, square root of 500. So I guess it's our 22 point whatever. Am I good by just saying 22, or should I go 23? 22 meters per second. That's how fast the cars are going here. So the next question is probably not what you're expecting. I'd like to know what the normal force is on the cars when they're at the bottom. Cars have a mass of 200 kilograms. There's a radius of curvature of 7.5. I'd like to know what the normal force is on the cars when they're at the bottom. This is not a particularly hard question, but it required part A to be done correctly first. And that's because for part B, net force has to equal MAC. The cars are traveling in a circular path starting right here. In order for the cars to be lifted upwards on this path, the net force has to be unbalanced. And there are 2 forces, normal pointing up and weight pointing down. Listen closely to this instruction. In dealing with circular motion problems, always make towards the center of the circle positive. That's a footnote, but an important one. Always make towards the center of the circle positive. So that has to equal mv squared over r. What people don't fully appreciate is that when things travel in a circle, it takes more force to get them to travel in a circle than just the weight of the object. You have to add this piece to it. This is what causes the roller coaster tracks to shake and move and sway. As the inertia of the cars pass through, they have to apply extra forces to keep them confined to the track. Now, this one's pretty easy. Asking you to find the normal force for a problem like this, pretty straightforward. You don't have to do much thinking about it. It's kind of a plug and chug. And this part is not new. The only new thing is changing how we calculate acceleration. That is the only new thing. that for an object traveling in a circle, we calculate the acceleration different. I'd argue that this kind of stuff is enough to get you a C on the test. If you want to get a B or an A, you got to listen to what's going to happen next. When the cars are here at the top of the track, there are two forces acting on them to keep them traveling in a circle. There's weight acting downwards, and there's a normal force acting downwards. If we make downwards positive, then that has to equal mv squared over r. So right now I'm talking about what happens at the top of the loop. This was the bottom of the loop. So this is where A is, and this is the top of the loop. Now, you guys tend to not see things unless it's really kind of put in front of you. So let me put this in front of you. We know that conservation of energy can decide how big the velocity is here. If I start the cars lower on the track, they'll have less velocity. If I start them higher on the track, they'll have more velocity. However, that also changes how much normal force there is. The weight of the cars doesn't change, but if I had started the cars higher on the track, then the velocity would be higher here, and I'd get more normal force. Now, something interesting can happen here. Because I'm adding normal force here to the weight, it's possible for me to start the cars lower on the track. If I start them lower on the track, the velocity will be less. And if the velocity is less, the normal force will be less.